Hello. Well, welcome back, everyone. Happy Thursday. We're pretty much just running the clock at the moment. Okay, looks like class can start officially. Welcome back, everyone. So for today's class, we're going to be finishing up the chain rule notes. We still have a couple tricky examples and a great suggestion to start us out today from the homework exercise in WebAssign. Then after we finish off the chain rule problem, we're going to move into our first pretty decently big application section, the section 3.6 on exponential growth and exponential decay. The subsection, Newton's law of cooling, it's very interesting content, but that one can be safely skipped. I'd say give it a look, but we're not going to cover those exact problems. They won't be part of the homework or the exams. After we cover this section, we'll probably finish it off when we come back on Tuesday. We'll move into 3.7, derivatives of logarithmic functions, and then finally move into chapter 4, applications of the derivative. Also, this Friday, after I get caught up on grading, I'll be posting the exam information, starting with the exact coverage, the formula sheet that will be attached on the last page, and all of the review problems as well. Well, any questions at all, folks, before we jump back into the chain rule? Okay, let's get started. And again, thanks to the student for suggesting this problem from the section 3.5 WebAssign. Some of those problems are really quite tricky for a variety of reasons. Sometimes the algebra is the most tricky thing about it. At other times, it's tricky because it's a combination of, say, a product rule along with a chain rule, along with a tricky function using the chain rule, an exponential, along with a tricky constant. So this one has like 4 or 5 different elements that makes it overall a very tricky problem. So to me, the thing that's kind of tricky here is that constant k. We've practiced with different situations where that comes up, but let's just put down a quick warm-up problem in dealing with that one. If you had a function that was written in a strange way, like say, let's use similar language, k, x cubed plus 6x plus 5, taking the derivative of this looks kind of strange. Think of that value k as just some other external variable or parameter that we could change to get a different type of function, but still regarded as being a constant. The variable in this is implied to be x, and so if k is a constant here, then finding the total derivative to this would be, let's say, dy dx, just to explicitly say we're differentiating with respect to the only one variable x itself. That reinforces that k here has to be a constant. Then we would use the constant multiple rule on this step. It'd be just a 3 times k. The new power on x would be 2. From here, this is a linear function with slope 6, so we'll get just a 6. And the constant function would go to 0 in the derivative. So I'd say this is already one pretty tricky element of the problem, having a non-standard constant. Think of that k as being like a number 3 or 5, anything along those lines. Much like this could have been, say, a 5 in that spot. We would have got 3 times 5 for 15x squared. Well, any questions, folks, with just the discussion of the non-standard constant we see there? Okay, next, if we're going to differentiate this whole thing, the first rule that pops out of this is not the chain rule. This is going to be the product rule. And I'm going to leave the blue and green color coding for the chain rule analysis. So I'm going to back off that step. But you can organize it kind of like this. Visually, there's a function 7x multiplied by a second function, e to the negative kx. Because the first function does depend on the variable x, a product rule enters the picture on this one. So if we differentiate this, I'll call it just a simple y prime this time. The setup would be take the first function, 7x, differentiate it, multiply it by the second function, e negative kx, then add to that 7x copied, and now e to the power negative kx differentiated. So that's our first level. We run through on this stage product rule, which means we still have to analyze two more derivatives. First one's not too bad. We just get a 7 out of that derivative. And this is the one that's a little bit more tricky. This is two functions really. There's an outer function, the e to the x, and then there's an inner function, negative kx. We do that function first, we do that function second. It's the first one I found. We do that function second when we differentiate. So that's going to be the inner one. But we actually differentiate this function first in the chain rule. So that's function one, inner is y equals e to the power of x, with parentheses around it, not because it's required or anything, but just to really emphasize there's more than x there. There's a constant multiplying it, negative k times our x. So now we absolutely have to hit this with the chain rule. So this is now the chain rule analysis on that part. And we're about ready to run through the derivative, but really just breaking it apart on a rule by rule basis is the hardest thing about all of this. Any questions at all, folks, getting to just this line? Okay, so now to finalize this, we have y prime, the derivative at x. First, it's a derivative of a linear function. So if it's x power 1, x vanishes and we keep the constant 7. E negative kx is just being copied. We can drop parentheses here and copy in 7x. And here's where it gets interesting. We're going to follow this chain rule formula verbatim as we see it on paper. But there's one way to see it as a formula and a whole nother way of seeing it as a particular function, whether it's a radical function, square root, fifth root, and so on, or an exponential function. They all look a little bit different. But thinking in these terms, if you know what the inner function is, you start by differentiating it. Here's the inner function, and the derivative of that, which is really just an e to the x, looks like this. E to power whatever goes inside there is the derivative of the inner function. Then we multiply, chain on a new derivative. That's this g prime at x part. And in both spots, we're going to put in the g prime of x. First spot is a copy, and the second part, we differentiate. So for this part right here, we put in that negative kx inside the exponential function's input slot, just where the exponent goes. We throw it in right here. That's the g prime of x portion, just penned in. And now we just have to navigate through that derivative. Again, it's not too different from this warm-up problem. It's x to a power 1. The constant will just be negative k, all we get after we differentiate. Here, we're done with the chain rule. We just have to finalize that last derivative there. Any questions at all, folks, getting to this step? Okay, so here's our, looks like probably the last line on this, depending on where we decide to stop algebraically. Y prime is, I'm going to copy all the way up to where the red dot is here. 7 e power negative kx plus 7x, e to the power, I'll drop parentheses, but no harm if you decide to keep them in. Negative kx here. And last derivative, differentiate this. No matter how weird the constant is, the constant survives because x is to power 1. So we get a negative k on that. And I believe WebAssign would accept this answer just as shown. You would definitely have to have parentheses here, or you're saying something different algebraically, subtracting k rather than multiplying it. But sometimes it's tempting to go one step further. Let's do it on this particular problem. Notice it has a greatest common factor of 7 e power negative kx. It's on the first term, and it presents itself as a factor on the second term. So if you take 7 e power negative kx out, that means you've divided here where the red dot is, leaving a 1, plus divide that same greatest common factor through here, and all it's going to survive is, I regret that plus, let's change it to a minus. All that's going to survive is going to be x times minus k, or you could just write it as minus k times x. That's just faster to type in, so sometimes taking a little bit of algebra is helpful for WebAssign as well. But that was a really tricky problem from WebAssign. I forget what problem that was. Let me put it on the notes. This was problem number 4. So if you give that one a try and you're having any trouble with it, come back to the notes to peek at how it goes, and it'll be really helpful getting through that particular problem there. Well, we're going to try out another chain rule. I would say number 4 is a little bit trickier than part D that we left on, but part D just looks a little bit more visually overwhelming algebraically, but not as intense as number 4. Any questions at all, folks, with number 4 so far? Okay, thanks again for suggesting that problem. I think that was a definitely great warm-up problem to start off the notes with. And that'll help folks getting through a pretty tricky problem in the homework exercise as well. Yep, you bet. And thanks again for suggesting it. Well, let's try out the next interesting one. After we get through this, we're going to look into another tangent line equation problem. And we're pretty much done with the section, but we'll definitely do the application at the very end. So this one's a little bit trickier because, again, it's absolutely a chain rule. But in the chain rule, we're going to have to take the derivative of what's on the inside, and that's going to become a quotient rule. So let's start just looking at the overall analysis on this. Let me blow this function up just a little bit. There we go. So there's 2 functions. And if we had to say first, what is the inner function? This one's not as tricky as, say, the exponential. I think the analysis on this one does require some training of our eyes to really pick it out. But if something's raised to a power or raised to a, say, square root, fifth root, and so on, the thing on the inside is your inner function, usually visually a lot easier to pick out. So there's function 2, inner. The outer function is just a power function, something raised to power 6. So that's function 1. Outer is y equals t to power 6, except we put in an entire rational function in place of t. So with that analysis down on paper, I'm sensing the need to put this on a different page. Let's put this on, let's put this on the next page just to make sure we're not cramming it in. So when we go through the chain rule on this, we'll say derivative of h, or h prime at t, is going to be first, do the outer, that's differentiating t power 6. And if you differentiate t power 6, it really looks like this. You put 6 down, we put in a humongous placeholder for where t was, put in a new exponent of 5, and this is pretty much the gist of the chain rule. Then you multiply by the derivative, put in another pretty big placeholder, you multiply by the derivative of the inner function, but at this stage, the outer derivative is done the moment we put this down. Times derivative of something is the chain rule part. And now, following the same exact progression of literally every problem we've done on the notes, some of them look different than this, but it was always essentially just this. Throw the inner function on the inside where we put in the placeholder, put it in the second placeholder, but then also differentiate it. So we're on our way with this. Only trouble is we now have a quotient rule, but that quotient rule is not too bad. We've done worse derivatives so far on these notes for sure already. Any questions on getting through just this chain rule step here? Okay, you know what I would do in this problem, because we already have a bunch of stuff in front, this is a good one to just divide up the problem. Let's work out the quotient rule, and then we'll plug it back inside here once we have all of this simplified. That way we're not carrying down this structure line by line by line for every single algebraic step and calculus step. So let me recopy this below. We're taking t squared minus 3, divide by t squared plus 3, prime. And how's the quotient rule go? Almost like the product rule, except there will be a minus on the inside, something to power 2 in the denominator. And I don't think I made that big enough. Let me try again with my fraction bar. That should do the job. So there's going to be a minus in the middle, something to power 2 in the denominator. We put in 4 placeholders in the numerator. Derivative goes on one, derivative goes on the other one. And then it's organized by numerator function, denominator function, or the top function versus the bottom one. T squared minus 3 goes in those positions. Once you have the numerator resolved, denominator goes in everywhere else. 3 positions for denominator. So t squared plus 3 here, here, and here. Then it's not so bad to work through the next derivatives. On the next step, where the red dot is, that derivative is just a 2 times t. They'll multiply t squared plus 3, subtract. T squared minus 3 is multiplied by the next derivative, clear over here. That's just another 2 times t, so I'll put down a 2t here. Then divide by t squared plus 3 to power 2. And it just keeps on going. Kind of rather have my equalities down here. Not a big deal where you decide to put them. Now we're distributing, simplifying as much as possible. We distribute that 2t inside the group. We'll get 2t cubed plus 6t. Here we're really distributing 2 things. Let's be more careful with this one. We're distributing a negative sign from the left, and we're also distributing a 2t from the right. Or you could just say distribute in negative 2t altogether. If you did that, you'll get right here, negative 2t to power 3, which is great. That's a cancellation. Then distribute again. That's going to flip the sign positive to 3. Then multiply by 2t will give us plus 6t again. All that's divided by t squared plus 3 power 2. We have these like terms going away. 6t plus 6t gets us up to 12t. Divide by t squared plus 3 squared. Okay, so we're done with the quotient rule. Notice that visually looks like it was way more work than the chain rule, but the hard work of the chain rule is just doing the analysis of what function is what in the composition, and then laying down the structure. So I would say this is the tricky part, and this is just the crank it out step, getting through the quotient rule. We're going to put in place of here, prime and all, just that. Any questions with where we're at so far? Okay, let's also do just a little bit more. You might have noticed there's a t squared plus 3 in the denominator. You know, that combines with this base, t squared plus 3 to power 2 in that denominator. So there's a kind of fun, clean way to write this. You could say h prime at t is equal to power 5 raises both the numerator and denominator to power 5 at the same time. So in the numerator, you can take the 6, t squared minus 3 to power 5. Then the denominator, t squared plus 3 to power 5. Multiply it by the result from the quotient rule, 12t. Then t squared plus 3 to power 2. Let me highlight that in yellow just to show where it came from. Then if we multiply across numerators, we have 6 times the 12 for a 72t. T squared minus 3 to power 5. The denominators, we can combine the like bases to make this t squared plus 3 now to power 7. So it actually kind of came together in a nice sort of clean way after doing, this was a bit of tricky algebra here, coming from distributing the exponent and then combining the denominators together for power 7. But any questions at all, folks, getting through that conclusion here? Naomi says, so you wouldn't be able to leave it as just multiply. I would say if you left it, say, like this, or even in this format right here, that would have been okay with me. So let's say an alternate answer, h prime of t is just fine left as 6 t squared minus 3 to power, divide by t squared plus 3 to power 5 times 12t t squared plus 3 squared. That would have been a totally fine answer as well in that format. It's compressed a little bit here, but again, the danger is it was extra algebraic steps. So if I made just one small algebraic misstep, I could have lost the total question, even if I had the right answer here. But you know, in an exam setting, if I saw this and you made a mistake getting to this, I would have given full credit on this step right there. Other questions at the moment? Okay, well, so far we've looked at a lot of stuff with derivatives. We've started with the power rule, then we extended all the way to the bigger tools like the product rule, quotient rule, chain rule. But the next example, what it's really all about is just a reminder. Anytime you calculate a derivative, what you're really finding is the slope to the tangent line of the original function at any input value for t. And it's easy to kind of get lost in the weeds when we've done so many interesting kind of convoluted derivatives like just this one right here. So the next example's purpose is to bring it back down to reality. It wasn't the next example. That's this one down here where we're going to do a tangent line equation. But apparently I forgot to have another example before we get to this one. So let's get to the tangent line equation after that example. So here's our, I think these might be misnumbered. That's our second example 3. Let's just call it part 2. So here's our next example 3. We briefly looked at this formula before we ended class on Tuesday. The idea is, something kind of broke here. Let me call that a y again. If y equals e to the x, the derivative is e to the x again. But the real formula that involves any exponential goes like this. The derivative of a base b exponential, b has to be positive, it cannot be 1 for it to be a true exponential function. It comes out like this, b to the x times natural log b. So if you're differentiating this one, you don't get to just 2 to the x, you get 2 to the x times the natural logarithm of the base, natural log 2, altogether. So we explored how some of these kind of combine now, and they sometimes can make us sort of hallucinate and get the wrong answer when we have all these rules coming together. The first function was a power function. So when we use a power rule, we just get 3x squared. But this function doesn't go like the others. X does not come down. You don't get x minus 1 as the new exponent because this is no power function whatsoever. It's an exponential function. When we differentiate 3 power of x, you get 3 power of x back multiplied by a new constant, the natural logarithm of 3, following this process. So that makes these two problems together very tricky. That's why we're putting them down side by side to just kind of train our eyes to spot the difference. But the challenge problem is this one. This one's a chain rule, so we'll work through this one carefully next. First, any questions at all, folks, with the refresh on these two problems? Okay, let's write this down as y equals 9 to the power. And even though there wasn't parentheses, you can always insert parentheses if you like. And I think it's helpful here because we're putting inside the original 9 to power of x exponential function. A new function goes in there, 3 minus 5 times x power 2. So that's a complicated function composition this time. The inner function is this one. So that's function 2, inner. And the outer function is the base 9 exponential. Similar to the question we started out today with the y equals e power negative kx problem. In both cases, the base is the outer function. I'll just briefly call this outer. So that means if we go to differentiate this one, y prime, here's what the format would look like. First, we're differentiating a base 9 exponential function. Following the format as we see it above, what you get is 9 to the power of x. But then there's more to that story. You have to multiply it immediately by the logarithm of the base, which is 9. So times natural logarithm 9. And that's the total derivative of the outer function. But the story isn't over because we have a chain rule. So then we multiply, hang on, that's not quite right. Sorry, I got a little bit lost here. We shouldn't put x in that position because in place of x, we're putting in the entire inner function. Let me backtrack a little bit. Should really go like this, 9 to the power of, sure, it's x in the formula above, I was looking at too literally, but that's not our situation. We have not x, but 3 minus 5x squared. So I should have plugged in a placeholder like that. Then it's times natural log 9. And then we can say times something per the chain rule. So sorry for backtracking on that bit right there. The chain rules can be pretty tricky, especially with exponential functions, and this one definitely tripped me up. Does that make a little bit better sense with this format so far? Okay, so now at that stage, with everything in blue, we've done the outer function derivative, but you don't want to put in the variable. We also put in the chain rule part, chain on a new derivative. And in both positions, we're throwing in what we called the inner function in the composition. 3 minus 5x squared goes both here and here. That's really cramming it in. Let me see if I can write that in just a little bit better. That should give us the right real estate to fit that whole thing. 3 minus 5x squared. Okay, I think we've got it in. I should have made more space for this third column. Once we're here, we're effectively done once we take care of that very last derivative. So we have altogether y prime is 9. I'll drop parentheses here, but no harm if you leave them. 3 minus 5x squared times the natural logarithm of 9. Now when we differentiate this group, constant 3 goes away. Power rule here is going to give us just negative 10x. So don't forget parentheses because we have to multiply by that. And at that line, we have the whole derivative. It looks kind of wonky with having the negative 10x here and the constant. You could rearrange it if you like. If you decide to rearrange it, some people might write this in as y prime equals negative 10x, natural log 9 times 9 to the power 3 minus 5x squared. But that's just really a stylistic choice. There's no algebraic difference between the first line and the one down below. I'll leave it up to you, and WebAssign isn't picky either on these formats. So I'll leave it up to you how you'd like to end the problem on. Well, exponential functions, again, are what make the chain rule tricky. But any last questions on getting through this one? You know what he says? Where in the equation does it tell us to multiply by the derivative of the inner function? I thought we just did the number b. Let me pull the definition to track through with that question. So let's place it here and let me reread. So where in the equation does it tell us to multiply by the derivative of the inner function? So I think you're referring to this part right here. And that comes from this portion of the definition for the chain rule derivative here. So once we've spot what's inner, the g of x, for us it was 3 minus 5x squared, we take the derivative of the outer, put the inner function inside, and this is the part where you're assessing where do we multiply by the derivative of the inner. So it goes from here to this part right here. Does that make sense with that question there? Yeah, exactly. We use the b of x equation right here when we wrote 9 to the power of something. I erroneously wrote x first on my first attempt, but we also had to include the natural log of 9 for the entire thing here. So we started with that equation. That was just the derivative of the outer function, essentially. Then, after we had that part, the derivative of the outer function, per the formula above, we plugged in the g of x function here, and we plugged it in here, that's this spot in purple, but also differentiated it. So this portion right here, let me switch to indigo apparently. This part right here is essentially just that part, the derivative of the outer function. And it came in on paper here. The only thing not really emphasized is the copy part. Here's where we copied in the inner function. So let's throw in a new arrow. And we went from here to here, copying. Again, lots of stuff to look at whenever you're doing a chain rule, in particular with exponential functions. In particular, if it's worse than e to the x, say 9 power of x, the formula changes even more on us. So lots to keep track of. Does that help with that analysis so far? Yep, you bet. Thanks for asking about that. Other questions at the moment about getting through this one? Okay, well, here's the next problem where I thought we were about to do before we got to finalize this one here. It's a throwback from problems we were doing earlier in chapter 3 of finding a tangent line equation. And again, it's just also a big reminder for us that we aren't doing anything different, no matter how crazy our derivatives get, like the very last one we just did. We are still getting the slope of the tangent line at any value. So here's a kind of nice function. We had a formula that we put down on paper, I think it was in section 3.4. Whenever a square root function comes up, you can say the derivative with respect to x of square root x. You can change the exponent to 1/2, then 1/2 comes out of the problem. New power is x to the negative 1/2, which can be thrown into a denominator. And the end result is you just get 1 over 2 root x each and every time you differentiate a square root. Pattern changes for cube root and so on, but this is the square root pattern. So if we combine that with this right here, and we're trying to get a tangent line equation, I would use this as we see it on paper to help out. And this is the step 1, same steps as what we've done before in getting through this process. The first step is just differentiating whatever the function is. I'll call it either a y prime if you prefer, but on the notes I'll go dy dx this time, just to practice Leibniz notation. But here's where the drama comes in the problem. This is not your ordinary function. There are really two functions there. There's the inner function, 9x minus 8, and the outer function, which is tricky to highlight, that square root we see. Haley says, would it be 1/3 root x if it was cube root? Yeah, absolutely. For a cube root, if you say y equals cube root x, you could rewrite this as x power 1/3. And actually, it's a little bit different now that you've mentioned that. I'm glad you asked that question. This is a nice clean pattern for the square root, but it starts to get a little bit more messy for the other roots. Let's see what happens on this one. Differentiate x power 1/3. You get 1/3 x to the power of, you have to subtract 3 over 3, so now it's negative 2/3. So then it becomes 1/3 x to the power positive 2/3. But that means altogether, if we bring this back in radical notation, it's 1 over 3 cube root. Those are the parts we expect. But then a surprise shows up. X squared goes inside of there, coming from the exponent 2 right there. So this is like the nice one. Root x, the root goes in the denominator, you multiply it by 2, and we're done. cube root x, fourth root x, and so on start to get a little bit more messy with unpredictable exponents. But the reason this one's such a nice formula is square roots are involved with distances, Pythagorean theorem essentially. So this one just shows up a lot more often than, say, like a fifth root in applied problems. Yeah, absolutely. Thanks for asking about that one. It's kind of surprising when the formula just sort of breaks down in like this case down below. So now in this arrangement, it's kind of hard to highlight the radical bar, but we can still say 9x minus 8 is the inner function, and the outer function is y equals root x. I'll just write it in blue as a way to sort of highlight the square root bar this time. So now if we differentiate that square root, we're absolutely going to be using the chain rule, but the first derivative we take is for the square root. It has that format. We just don't use x. So differentiate the outer, and we get, let me go back to blue, 1 over 2 square root of something. You could put a parentheses there, but the square root is already associating something. It's an implied group. Then we multiply by the derivative of whatever the inner function is. So there's our chain rule. We've taken care of derivative 1. Now what we do, every single time we've used a chain rule, we have 2 placeholders. That's our first one. It just looks different because it's a radical. And that's our second placeholder. So copy 9x minus 8. I want to use green just to emphasize the inner function. We'll copy here and here. So it's in those 2 positions as needed. We need to simplify this derivative down. So dy dx is now, let me copy the denominator first, 2 times root 9x minus 8. This derivative just turns out to a 9. And when it multiplies a fraction, it just multiplies up into the numerator. So all we get is a 9 from the derivative of the inner function. And there it is. It's almost like that, but if you have 9x minus 8, 9x minus 8 goes inside there, and its derivative, just a 9, goes up in the numerator. So that's a nice, fast, clean way to handle and whatever square root might come up. This makes it a pretty nice, reliable formula for square roots only. Once we get done with step 1, step 2 is just to get a slope. But any questions at all, folks, on what we did for step 1, the chain rule part? Okay, so we have a derivative. We use some complicated tools, the big power tool chain rule, to work through it. There's no other way to do this because unlike, say, a power 2, I can't distribute a power of what's effectively 1/2 into 2 different terms. That's one of the mysteries of algebra. There are ways to do it, but you get infinitely many terms, and you have to use something called the binomial theorem, so it's just no helpful for us. But now that we have that, we can get the slope by plugging in the x coordinate, 1. So we say, take your derivative, dy dx, input, x is 1 inside of it, coming from the first coordinate, we'll get that this is equal to 9 over 2 times root 9 times 1 minus 8. So all we do is plug 1 into the derivative, and we get a slope out. That's what our derivative is providing. In our denominator here with the root, that's just square root 9 minus 8, which is square root of 1. So it's just a glorified 2 times 1 in that denominator. We have now slope 9/2. And then we're essentially done. We just need to build the actual equation. That takes us to step 3. Our tool for building the equation goes y minus y1 is a slope m, which we just found, times x minus x1. The original point 1, 1 is our x1, y1. So plug all that in to the right slots, and we're through with the problem. So the big analysis is the derivative provided the slope to the tangent line. So now it's y minus 1 is 9/2 times x minus 1. We still have to do a little bit of algebra on it to solve for the y variable. So I'll write this as y minus 2/2. Distribute 9/2 inside for a 9/2 x minus 9/2. Then add 2/2 to both sides. Y equals 9/2 x minus 7/2. So here's our entire tangent line equation analysis. Well, it's the tangent line specifically at the point 1, 1, or a tangent line when x is 1. Any questions at all, folks, getting through all the algebra there? Okay, we've looked at this before, but the fun thing about a tangent line equation problem is you can always get a really reliable numeric check on this. You put in the original function, y equals square root 9x minus 8, and we're concerned about the point 1, 1. So right here, we want to know what is the rate at which the curve is increasing right exactly there. It's pretty steep in this location, so we expect a steep slope. And it was. It's saying it's increasing by 4.5 units for vertically for every 1 unit horizontally. That's what this slope is telling us. Then if we are really concerned about the concept of what is the tangent line itself, we will just plot that line, y equals 9/2 of x minus 7/2, and you get this picture. If you zoom in on this a lot, the idea with the tangent line is it's approximating the whole entire function locally when x is 1. It's the best local linear approximation for the x value being 1, in the sense that I can get as close to the function I would like by taking the x values as close as we would like to 1 itself. Or in other words, zoom in far enough and the functions become indistinguishable. They are different if we're out here. They only match exactly at 1, 1, but it's the best approximation you can ever discover locally near the x coordinate being 1 itself. Well, that's kind of a fun throwback problem, just reminding us what the derivative was really all about. And we'll look more into these kind of concepts when we're in chapter 4, applications of the derivative. What we'll do next is look at one more application. So this one is about blood flow, making it pretty relatable. We're all living human beings, so this is something that keeps us alive, the fact that blood flows at all. But it has something more going on with it. A drug is administered and an artery begins to dilate. Dilate means grow larger. Say, if your pupils dilate, then they become smaller. Well, they look smaller, but they get wider as they're dilating. We're told here the speed of blood, that is r centimeters from the center of an artery, is given by this equation. So human anatomists, biologists have worked really hard on this problem. C is a constant. That's mysterious, but they provide the constant, so that helps us out. R is the radius of the artery, so it's some radius. S is measured in centimeters per second. It's a rate of speed. So they told us again it's a speed. This is the speed of some blood platelet if it's a distance r from the artery wall. So if I'm right here, this arrow is trying to give us a visual, a graphical representation for the speed of that blood platelet. But there's more going on in this problem. It's more dynamic than it seems at first. A drug is administered and the artery begins to dilate. And there's lots of drugs that do that for medical reasons. It's dilating at a rate dr dt at a constant distance r. So r is another constant. Let's organize our constants. We have a constant here, lowercase r. That means we're only worried about a blood platelet being some fixed distance. It's not going to move up or down. We're imagining just right at that spot. C is a constant coming from just the human anatomy, biology of the problem. We want to find the rate at which S, the speed of the blood, changes with respect to time, for that specific constant, for that specific radius of the blood vessel, and if the blood vessel is dilating at that specific rate, growing or expanding at that rate. Chain rule problems in a biology setting like this are kind of messy. So let's take our time working our way through this. What is the variable? Well, we said C is constant. We also said lowercase r is constant. But what's changing? The artery is dilating. That's our variable. The radius of the artery itself is the variable. So let's take this function. It's written in a certain way that might be appropriate in some contexts. But for the purposes of a derivative, I think it's easier if we just distribute C inside that group. We can write the speed of the blood platelet, S, is the constant C. We know the constant is down below. They didn't tell us the units. I should look into that. This was copied directly out of the textbook. No units were supplied. It's C times R squared minus C times lower R squared. But this is a total constant right here. It'll go to 0 when we differentiate it. And this is a constant times a variable, much like x to power 2. When we differentiate this, we'll just get to 2 times c times r power 1. Well, here's the tricky part of the problem. It says, find the rate at which s changes with respect to time. Let's come up with a good color here. How about turquoise will do the job? When it asks us to do that, what it's really telling us to do is compute ds dt, the rate of change of the speed. A rate of change of speed is effectively acceleration. So we're trying to ask the question, if we take the right drug, some kind of nitroglycerin type drug, the artery dilates, what is the acceleration on the blood platelet as it's dilating? It's a pretty big involved problem. There's a lot of context. Any questions at the moment so far? Just delving through all those moving parts. Okay, well, with that on paper so far, notice our derivative is written in Leibniz notation, and it's also a chain rule problem. If we go to differentiate s with respect to t, that looks funny no matter how you write it because there's no t there. But t does enter into the question because you're taking a drug and the dilation of the radius of the blood vessel depends on time. That's the inner function of the process. So when we go to differentiate ds dt, what we get in Leibniz notation is ds dr, the derivative of the outer function. But that r there, the radius of the blood vessel, is dilating with respect to time, so we have to multiply that by dr dt. And this part's the derivative of the inner function. And notice we kind of looked at this problem. It's the first problem in the notes. If you thought of these as fractions, they're not, but it's a good analogy. Those would cancel and you get back to ds dt. This was really just the first problem we looked into in the notes. So if we analyze this, the first derivative we take is the derivative of that whole thing, s. If we differentiate s, the constant part goes to 0 right here, and you just get constant multiple rule, say c copies down. Power rule on a variable r, much like s, would have the constant 2 drop down, and r is to now a power 1. Naomi says, would this kind of problem be on the exam? I would say no, because we really focus more on the chain rule, not in Leibniz notation. So this is a kind of problem that's going to come up a little bit more in chapter 4, where we're going to get more practice on, but not for exam 2. More of a preview of what they're going to look like for some problems in the next chapter. We'll focus more on Leibniz notation as written here, and doing the chain rule in Leibniz notation like we did here. But definitely an unfair exam problem, I would say. Well, we've got the derivative of the inner function. We multiply it by the derivative of the inner function, dr dt. Well, here we're told that if the drug is administered, the artery begins to dilate. That would be the R right here. R is not constant. It depends on time t. And the value they gave us for was, we were wanting to know what is the speed of the blood just at a specific number. So although we have a value for R here, like you spotted, we're thinking that we could just change this number, ask what would happen as a little bit more time went by, and it's a 5 instead. We'll get a different answer out for the derivative, a different acceleration on that blood platelet. So R varies. We're just saying, what is the derivative at a specific value for R? Much like in this problem right here, we were asking, what is the value of the derivative at a specific value for X? We plugged in 1, we got the constant 9/2. So analogously, we're going to do a derivative, dr dt, but we're just going to plug in that value, and also for a specific value of R right here. Does that make sense with that so far? Yeah, you bet. Definitely a challenging question, so thank you for those questions so far. Other questions at the moment? Okay, well, let's plug in the constants. We're effectively done with the derivative right this step. And it's a really challenging one because even if we know that R is the variable of the problem, and we differentiate this either in that form or that form, the surprise is you're being asked to find the rate of change with respect to time. So ds dt gives you a derivative for R, but then the chain rule says you have to multiply also by dr dt, and that's this part right here. So they're saying, what is the value of the derivative? This is the evaluation part. When we have a value for the constant, we are only looking at one specific radius, and assuming the drug is dilating at that particular rate for the time in question. So if we plug in all of those constants, we can say this comes out as 2 times by for C is 1.76 times 10 to the power 5. Then we're multiplying by the evaluation. R is 1.2 times 10 to the power -2. So all that stuff came from this part right here. And we're also saying we have a value for dr dt. It's exactly 10 power -5. So go times 10 power -5. And we're going to throw that into a calculator, see what it is. But this also has units. S itself is measured in centimeters per second. So even though the textbook didn't supply units on any of these, it's kind of rude. We can't do any unit analysis. Leibniz notation back here provides the units. Unit for S, because it was a speed, is centimeters per second. So there's a unit for S. But there's also a unit for T. This is measured in seconds, so we can say centimeters per second. And that looks kind of funny, but that's the right thing. An acceleration is really centimeters per second squared. In an acceleration, you have the unit, time unit squared all together. So let's plug this into the calculator, finalize the constant. We have 2 times 1.76 times 10 power 5. 1.2 times 10 power -2. If I can get back there, there we go. And this is one of those calculator problems where we need a lot of horizontal space, times 10 power -5. And this is acceleration, 0.04224. In units, centimeters per second squared. So this is the rate at which the speed is increasing or the velocity is increasing. This is the acceleration of the blood platelet when the artery is dilating, and if it's dilating at that specific rate, and only when it's dilated to that specific radius do we get that number. Change anything about the problem. Maybe you're saying again, it's dilated to that radius. We're going to get a whole different value rather than what we did before. And maybe the patient responds differently to the drug. Maybe it doesn't go at this rate. Maybe it's a slightly different rate. That would change this value here. But if everything is exactly right in this model, that's acceleration of the drug, or excuse me, that's acceleration of the blood platelet. If it's right here, specifically this distance away from the wall of the artery, which is also expanding. Well, any last questions at all, folks? Getting through this problem here? Okay, this tells us a lot of stuff biologically. Notice when we went through this whole problem, the actual distance from R, lowercase r, didn't factor into it one bit. So every drug platelet, no matter how close or far away from the wall, it's all accelerating at that same exact rate. So that's kind of interesting what that's saying also on its own right. But that was our big example for why we need chain rules. If we're doing anything just a little bit more complicated in a real applied problem like this one, it gets messy, the derivatives are tricky to analyze, but we'll be practicing this more in the upcoming chapters, chapter 4 in particular. Well, we have another application we're going to try to take a look into. I don't have a lot of time to get too far into this application, which is a little bit concerning to me because quiz 6 is based off section 3.6. I need to be a little bit more careful writing these. I'm going to try to write my quizzes so that they're going to be assigned on sections material that we actually complete. We took a little more time on the chain rule. So what I'm going to do this time is, just so that you're not worried about doing a quiz for content we haven't gone very far in, I'm going to change the due date on this one. It's going to be kind of a catch-up week, I guess we could say, on quizzes. I'll make this one due the Thursday of this week here. Only because it's, again, based on the next section. Let's take a look into that next section. Kind of follows the theme of what we were doing so far, looking into applied problems. Applied problems do get messy, so we're going to take our time just starting off this one before we get to the nitty-gritty details of exponential growth and exponential decay. The interesting thing about these problems, let's kind of scroll down for just a moment, is as far as it comes to part A, this is kind of a review problem for us. In a pre-calculus course, we look into exponential growth and decay models, and we do this problem right here, part A. Part B is also a review problem. It's just an evaluation of the model, the number of cells. But this is where the calculus starts. If you're being asked a question, growth rate, that's a derivative. Here we're using calculus. So that's going to be always the tricky part of the problem that we're looking into. So keep that in mind as we do the notes. Good bit of it's review, but whenever you see a word like rate, either a growth rate or decay rate, you're talking about a derivative, an instantaneous rate of change, which is effectively just a slope. Okay, let's get back to the definition. We have a derivative in Leibniz notation, much like the problem we just got through. That's kind of a little bit nice of connection there. We have a complicated looking exponential function, but hey, we differentiated that as our very first problem of the day, so that was a great one to start us off with. And let's read through what this is all saying together. If y of t is the value of a quantity at time t, maybe it's a population, maybe it's a amount of mass at a given time t, and if the rate of y, change of y with respect to t, is proportional to its size y of t at any time t, then you get that. This is an interesting differential equation. And even though this is not a differential equations course, you just can't avoid these in calculus. A differential equation means it's an equation we wrote down that involves a derivative. That's the dy dt. And in a differential equation, the unknown is the function y equals f of t. So we know the derivative of the function. We don't actually know the underlying function. That's the context of a differential equation. It says the rate of change of y with respect to t right here. But when you say that, recall rate of change, it just means derivative. And that's why we said dy dt. This is just a verbal way to say the derivative of y with respect to t. And here it is, y prime, but in Leibniz notation. We're also being told it's proportional to its size, y of t. That's the y part right there, at any time t. Proportionality requires a constant of proportionality, and that's what this k value is right here. K is a constant, referred to as the relative growth rate if it's positive, or relative decay rate if it's negative. But if you're thinking in terms of just ordinary proportional equations, if you say something is proportional to y of t, you get that equation, and k is called the constant of proportionality. Pre-calculus sometimes covers these concepts. Other times they skip it if they're running behind on the course. So no worries if this feels like it's kind of new material. It will still be just fine in the notes. So we'll call this the law of natural growth, or just exponential growth for short if k is positive. Law of natural decay, or just exponential decay if it's negative. Well, any questions at all, folks, about the underlying differential equation here? Okay, because it's not a differential equations course, we're not going to solve this using first principles and first methods, but there is a process to solving this called separation of variables. You can rearrange this thing as a algebraic tool. It's a weird step, and then do something called integration, and you get this out. This is the solution. The unknown was a function, and here's the actual function. We're told for theorem 2, the only solutions possible to this differential equation are that a function that goes y of t equals y naught times e to the power kt. Notice that k comes up again when we find the solution to the underlying differential equation. So we have two interesting values. K, the constant of proportionality, or I'll just call it a growth rate or a decay rate. Relative is an important word there, so I'll try to remind myself to say that as well. But there's another interesting quantity, this y at 0. This one's called the initial value. If y is, say, a population, or if it's a mass, or if it's an amount of money even, that's going to be the initial population size, or the initial amount of mass, or the initial value of money, whatever quantity it might happen to be. So we have a differential equation. We're going to use this when we answer the calculus question. We were looking down there on the notes later on. But now that we know the solution, this is what you primarily would have been studying in a pre-calculus course. And here's a really fast problem without very much context, other than we're being told it's a population size of a country. We don't know the country at time t. We know it's measured in years. So for this altogether, we have two interesting values. The 750, and that's a positive quantity there, so we'll call that a relative growth rate. It asks which portion of the function represents the relative growth rate. That's always this portion right here. Recall it is a constant, so it doesn't involve the variable t. We would just say it's k equals 0.235. Next part of the problem says, which portion of the function represents the initial population size? That's another thing we can just visually spot directly by looking at the format of the function. should be a 750. Yeah, absolutely. The initial population size is exactly that. You could call it y at 0, but at the end of the day, it's exactly like you said, a 750. So you'll have y at 0 is 750 for the initial population size. And you know the thought on that one, if this looks kind of vague and foggy, it's what always goes here. And the reason for that is if you evaluate y at 0, you're literally plugging in 0 right there for the variable t for time. You would get 750 e to the power 0.235 times 0, but then that just becomes e to the power of 0. E to the power of 0 is a 1, so you just get 750 right away. So the short of it, just like you said, 750 is the initial population size. And now this is the calculus question. Recall we have a differential equation there. We're just being told that if we consider the differential equation, that format of a function is the automatic solution. And we happen to have a function just like that. We want to verify once and for all, is it true that the differential equation, the rate of change of the population at time t, or p prime, or Leibniz notation dp dt, equals k times p. So let's take a look into that and see just what happens. This is effectively going to give us a humongously important formula because it answers the question here. If you find the growth rate, it turns out you don't have to differentiate the function part A because the differential equation itself was always the known thing. The function is the unknown, the solution to the equation. So we're going to effectively check if we really have the solution to an equation, much like if you're solving 5x plus 3 equals, say, 0, checking the solution by plugging in the value x. Here's how it goes. We'll go dp dt. That's the original differential derivative portion of the differential equation. But for doing dp dt, that's just the derivative with respect to time, d dt, of this function, 750 e to the power 0.235 t. So we have two rules we have to navigate. First, that's a constant, so it's a constant multiple rule, definitely not too bad. Next, that's going to involve a chain rule for sure. So we'll need to be careful on that end. So let me do these rules one at a time. We can say that this is 750 times d dt of e to the power 0.235 t. So if we take that step there, all I've done is the constant multiple rule. The derivative of a constant multiplying a function is the constant multiplying the derivative of the function, as we now have on paper. And if we differentiate this, we'll have to be a little bit extra careful. And also my color coding are more about the initial value and the relative growth rate. So not the same color coding we did in the chain rule, but the organization is still the same. That function right there is the inner, the function going into the exponential function. The base e exponential itself is the outer function. So outer is y equals e to the power of x. Let's say t, because that's the variable this time, e to the power t. So if we differentiate that, here's what we're going to get on the next line. This equals 750. Differentiate the base e exponential. There it is, that derivative is done. Now, we need to differentiate the inner function. It's just a linear function, 0.0235t. And that inner function goes in both of the placeholders that we opened when we differentiate the outer function. It'll go here, let me try again, 0.235t here, 0.235t here, and we're just about done with it. But if you're looking at this really, really carefully, Notice the interesting thing that's happened. The mathematical miracle at the moment is the first two factors put together is just the original function p of t itself. All of this is p of t. That's kind of an interesting thing that happens. And that's the p part right here in the differential equation. We need to do one more derivative, but when we do that, t comes off, and we're left with the k value. This is all that's going to survive, highlighted here, when we differentiate t power 1. So on our next step, we can rewrite this as equals, I'll do this portion, the derivative. The last derivative remaining, that's just going to be a 0.235. But this whole entire piece, coming back to the top, is p of t. Next, 0.235, that was just k. So this turns into k times, that's a horrible k. Let me start over with that. K, I'm in trouble with the letter k. One more try. K times p at t is the result. So we started with dp dt. That was the left-hand side of the differential equation, but we did the derivative from scratch. We cranked it out. We had to navigate a tricky chain rule. But when we came out the other side, we found the function came out again. There it is. And after finalizing this chain rule step, the relative growth rate popped out too, right here. This verifies this as a mathematical fact. We start with this as the solution and differentiate it. That's the inevitable conclusion. dp dt is the growth rate k times the population size p. It's a tricky derivative for sure, but any questions at all, folks, getting through it this one time? Okay, here's the value of doing it this one time. You actually never have to reinvent the wheel on this. Even if this was a p of 0 or a y of 0 and e to the power kt, if you differentiate this one, it goes the same exact way. It's more complicated because it's more abstract looking with its constants. If you did that derivative, say you differentiated whatever you got in part A, you will not have to reinvent the wheel. If it says growth rate, you'll just use the fact that dp dt equals k, we'll solve for that, times p. We'll want p at 2 hours, but that's what the prior step B is all about. So the calculus step is already resolved. That's the weird thing about these problems. We already know the differential equation. We just don't know what p is. Likewise, say in the next example, it's the same kind of thing. When it says at what rate is the sample decaying, we'll just use the formula from the one we derived with the particular example. The rate of change of mass, we'll use m for this problem, with respect to time, is just mass times, or k, the relative decay rate, times mass again. So we're going to reuse this idea quite a lot to get through the notes. And we're harping on this a lot because the easy mistake to make in a problem like this, in particular, say in an exam setting, is if you notice it's a rate problem, so you need a derivative, you actually don't have to do any of that at all. The derivative is already known in the first place. Differential equations are weird, and this is the way in which they're weird. It starts with the equation, and we're just being provided with a solution. Well, we'll come back to this when we're on our Tuesday's class. And again, because we just cracked open the notes really, I'm going to rewrite the due date on this one. So not a bad idea if you want to take some time to see how it goes in the notes. This quiz problem is pretty similar to example 2. Not a bad idea to wait until we finish off this example 2. Any last questions at all, folks, before we call it a night today? Okay, well, I appreciate your hard work. Thanks for the participation, the careful questions you've all been asking. The chain rule is the tough one, and we did a really hard applied problem as well. So congratulations on getting through it. Next section is definitely not too bad. And the next section after that is about logarithms. So we'll review a little bit about logarithms as we do it. It won't be too bad either. Have a great weekend, folks. We'll be back to it on Tuesday. Thanks. Have a good one. You too. Have a good one.